In this session, we're going to look at examples under degenerate kernels. So let's consider this example. Solve the integral equation y of s minus 2 integral from 0 to 1, 1 plus 3st y of t dt equal to s squared. Now let's start this. So solution. In our previous video, we said that degenerate kernels is a finite sum of pairwise product function. And so let's rewrite this equation. Y of s becomes, which is the same as, we need general form, so let's send this one to the other side, which is the same as s squared plus 2 integral from 0 to 1, 1 plus 3st y of t dt. So this side, if you compare it to the general form, the general form of integral equation, which is y of s to equal to f of s plus lambda integral from a to b k of st y of t dt. You can easily see that this whole part becomes your kernel. K of st is equal to 1 plus 3st. So our kernel kst is same as 1 plus 3st. And you are seeing that this is a degenerate kernel because it's a what? It's a finite sum of what? Pairwise product functions. So degenerate kernels can be written as a1 of s, b1 of t, then plus a2 of s, then b2 of t. We are having two terms here. So if you compare these two equations, you can easily see that a1 of s and b1 of t correspond to what? 1. So a1 of s and b1 of t is equal to 1, which means that a1 of s is the same as what? 1, and b1 of what? T is the same as what? 1. So 1 times 1 will give me what? 1. And the other side, a2 then b2 correspond to what? 3st. So a2 of s, b2 of t is equal to what? This 3st. So 3st. Then we are going to say that a2 of s is a function of only s. And so we can make the whole of this to be correspond to a2 of s. So a2 of s becomes 3s, and b2 of t is a function of only t. So b2 of t becomes, which is the same as t. So if you multiply b2 and a2, you're going to get 3st. So if you sum these two functions, their products, if we sum them, we're going to get our kernel k of st, which is the same as 1 plus 3st. So we've easily shown that this kernel is degenerate. Therefore, you can solve it by using the degenerate approach. So let's start. And so we're having our y of s from this equation, having y of s to be equal to s squared plus 2 integral from 0 to 1, 1 plus 3st y of t dt. Now we are having a sum here, so we can easily separate them into two different terms. So our y of s becomes s squared plus, so 2 integral from 0 to 1, then 1 y of t dt. So plus 2 integral of what? 0 to what? 1. 1 times y of t is the same as y of t. So y of t, then your what? dt. Plus 2 and the integral sign times this whole function. You're going to get 2 integral from 0 to 1, then 3st, then y of t dt. So you're now able to break this integral sign into two different integrals. So as we did in the exact method, let's bring all the function of s under the integral sign outside. Becomes y of s to be equal to s squared plus the next thing, which is 2 plus this here, 2 integral from 0 to 1 y of t dt plus, let's bring the 3s outside. So I'm going to have 2 times 3s integral from 0 to 1. Then there is t there, so t y of t dt. So we can, this equation becomes, so 2s, 2 times 3 becomes what? 6. We're going to have 2s s squared plus these 2 integral from 0 to 1 y of t dt plus 6x integral from 0 to 1 t y of t dt. So if you integrate it from 0 to 1, you can see that you get a constant. If you integrate this one from 0 to 1, you can see that you get a constant. So you can say that we should let our C1, to be equal to integral from 0 to 1 y of t dt. And this integral from 0 to 1 t y of t dt will still give you a constant. So let's represent it by another constant. Let's say C2. Now let's substitute our constant C1 and C2 into this equation. We are going to have y of s to be equal to s squared plus 2c1 plus 6s c2. Now you need to solve for our c1 and c2. But we have y of s here, we have y of t. Then let's change this s in the equation to t. So the equation becomes y of t to be equal to t squared plus 2c1 plus 6t c2. So we are having the y of t. Now let's substitute this equation into the c1 and solve for the c1. Our c1 becomes c1 is equal to integral from 0 to 1. Then t squared plus 2c1 plus 6t c2 dt. So you can easily see that if you integrate t squared, you get t raised to the power 3 divided by what? 3. So c1 is equal to t raised to the power 3 divided by 3 plus, if you integrate here, you get 2t c1 plus 2t c1 plus, if you integrate this side, you're going to get t squared divided by 2. So which is 6t squared c2 divided by 2. All this evaluated from 0 to what? 1. Now our c1 becomes, if you evaluate this at 1, you're going to get 1 over 3. When you put in 0, all here t's are inside, so all this one becomes 0. So once, so let's put in what? 1. Here becomes 1 over 3 plus 2c1 plus what? 6 over 2. 6 over 2 is the same as what? 3. So 3c2. Now let's bring all the constants to one side. So we're going to have c1 minus 2c1, then minus what? Minus 3c2 to be equal to 1 out of 3. So c1 minus 2c1 will give me what? Minus 1. We're going to have minus c1 minus 3c2 to be equal to 1 over 3. Let's name here as our equation 1. Now let's substitute this function into C2. C2 is equal to integral from 0 to 1 t y of t dt. So our y of t, let's put the y of t inside this equation. We're going to have our C2 to be equal to integral from 0 to 1. Then t into bracket t squared plus 2c1 plus 6t c2. So t squared plus 2c1 plus 6t c2 dt. Now let's multiply the t by each of the terms in the bracket. I'm going to have c2 to be equal to integral of 0 to 1. Here becomes t cubed plus 2tc1 plus 6t squared c2, then all what? dt. Now let's integrate. If we integrate t cubed, we're going to get t raised to the power 4 divided by 4. T raised to the power 4 divided by 4 plus, we integrate t, we're going to get t squared divided by 2. So here becomes 2t squared c1 divided by 2 plus, we integrate here, I'm going to get t cubed divided by 3. 6t cubed c2 divided by 3, evaluated from 0 to 1. So if you put 0, if you put 1 here, again get 1 over 4. So our c1, our c2 is equal to 1 over 4 plus, if you put 1 here, 2 cancel 2, so 1. So here becomes what? c1 plus c1. And if you put 1 here, it becomes what? 6. 6c2 divided by 3. But 3 will go into 6 times 2 times. So here becomes plus 2c2. 2c2. But if you evaluate it at 2, 0, all here becomes 0 because each of the term has t's in it. Now let's move all the constants to the other side of the equation. I'm going to have minus c1 plus c2, then minus 2c2 to be equal to 1 over 4. So this is the same as minus c1 minus c2 to be equal to 1 over 4. And let's name here as our equation 2. So if you're able to solve these two constants, c1 and c2, then you will be able to get the solution to that integral equation. So we need to solve for the c1 and c2. To solve for this c1 and c2, we've obtained these two equations, equation 1 and equation 2. We need to solve these two equations simultaneously. So it is a system of what? Equations. So we can put these two equations in a matrix form. The matrix form becomes, yes, minus 1, minus 3. So minus 1, minus 3. And here is what? Minus 1, minus 1. Minus 1, minus 1. Times the constant, c1 and c2. Which is equal to, the first term is 1 out of 3, then 1 out of 3, then what? 1 out of 4. 1 over 4. Now I'm going to use something called Parents' rule. From Clement's rule, we are going to from Clement's rule, from this side, let's represent this whole matrix as D. So D should be equal to the determinant of this matrix. And which will be the same as negative 1 times negative 1, give me 1. So minus, into bracket, negative 1 times negative 3 will give me 3. So 1 minus 3 is the same as what? Minus 2. So my d is what? Minus 2. And we need to find for what? d1. d1 means that if we want to find for the d1, which means that we're going to change this column to this side, this coefficient, this values 1/3 and 1/4. So this side you interchange them to have your d1 determinant. So d1 becomes (1/4) and minus 3 minus 1. It's the same as 1/3 times this one will give you minus 1/3. Then minus 2 brackets. This and this give me minus 3 out of 4. So this is the same as minus 1 out of 3 plus 3 out of 4, which will be the same as LCM is 12. Yes, minus 4. Then here becomes what? It goes into 3 times. So 3 times 3 is what? 9. So plus 9. So this is the same as this implies that d1 is equal to 5 out of 12. Now for the d2, let's interchange this second column to this values here. Then I'm going to have our d2 to be equal to minus 1, then 1 out of 3, 1 out of 4. Which is equal to, so the determinant this time this, we get minus what? 1 out of 4. Then this time this, so minus this time this, we get minus 1 out of 3, which is same as minus 1 out of 4. Then plus 1 out of 3, which will be equal to the LCM is still 12. Here becomes go to this for 3 times, so minus 3, then plus 4, which is same as 1 out of 12. So d2 is this. And you have all our determinants from that system of equation. And c1 is the same as d1 divided by d. My d1 is given as 5/12. So 5 out of 12. So divided by, and d is given as minus 2. So let's put minus 2 here. Divided by minus 2. So here, if we do your equation very well, you're going to get minus 5 out of 24. That's for C1. So C1 is equal to. Now my C2 is the same as D2 divided by D. And D2 is what? 1 out of 12. And divided by the D. The D is given in the question as the D is minus 2. So if you do it very well, we're going to get minus 1 out of 24. Alright. Now we have our C1 and C2. Now our C1 and C2. Now let's substitute the C1 and C2 to this function. That will be the solution to the integral equation. So y of s becomes s squared plus 2 into bracket C1 is minus 5 over 24. Then plus 6s into bracket C2, which is same as minus 1 over 24. So y of s becomes s squared plus, so minus, so 2 cancels 24, how many times? 12, going to 24 12 times. Then we cancel minus 5 out of 12. 6 cancel itself 1, cancel 24, how many times? 4 times. So here becomes minus s divided by 4. So this can rewrite the solution as, then you can rewrite it as y of x to be equal to s squared minus s divided by 4 minus 5 out of 12. So this will be the solution to this integral equation, which has a degenerate kernel. So this is the next example I'm going to look at. This example 2. Solve completely the integral equation below. Y of s minus lambda integral from 0 to t, s of t, y of t dt equal to f of s. And where lambda is equal to 1 over 2 and f of s is equal to 1 over 6x, show clearly the resolvent kernel and the radius of convergence. This particular example, we solve it using the opposite method, using the kernel to what? To find the approximate solution to this integral equation. But this time around, we're going to solve it under degenerate kernels using the how to manipulate, the way you use to manipulate the exact method, the same format, and now generate our resolvent kernel out of that. So let's start. Alright, the equation is given as this. So let's rewrite this equation as which is equal to lambda, which is equal to f of s plus lambda integral from 0 to 1 st y of t dt. So let's factorize the function of s out because it is a constant under the integral sign, because we are integrating with respect to t. So y of s becomes f of s plus the lambda s integral from 0 to 1, then t y of t. Now, if we integrate this, I'm going to get a constant. So why don't we represent this side by a constant? Let's say c. So c is equal to integral from 0 to 1 t y of t dt. Now let's substitute this c to this equation. So y of s becomes f of s plus lambda sc. Now we need to solve for this c, but we know c to be equal to this, integral from 0 to 1 t y of t. So let's interchange the s here to t. Y of t to be equal to f of t plus, let's say, lambda c t. Now let's substitute this to this equation. And we're going to have our c to be equal to integral from 0 to 1, then t, and y of t is f of t plus lambda ct dt. Now let's open up this integral. So this integral 10 by 10. Our c becomes, c is equal to integral from 0 to 1 t f of t, then dt, plus integral from 0 to 1. So this t times this. So we're going to have lambda ct squared. So integral from 0 to 1 lambda c t squared, then dt. So this is the same as c to be equal to integral from 0 to 1 t f of t dt plus, it's a linear operator, so you can easily bring the constant out. Lambda c integral from 0 to 1 t squared dt. We have our c to be equal to, so the first term, this is our first term, so we take it from 0 to 1. T f of t dt plus lambda c. If you integrate t square, you're going to get t cubed divided by 3. So t raised to the power 3 divided by 3 evaluated from 0 to 1. C becomes integral from 0 to 1. T f of t dt plus the whole of the t value, the whole of it, we're going to get lambda c divided by 3. So we are trying to solve for c. So let's send this term to the other side of the equation. We're going to get c plus a minus, so minus, so putting becomes minus lambda c divided by 3, which is equal to, it's equal from 0 to 1, t f of t dt. Now you can easily factorize out the c out. So if you factorize c out, we're going to have 1 minus lambda over 3. So 1 minus lambda divided by 3 all times c, which is equal to integral from 0 to 1 t f of t dt. This can be the same as, so the LCM itself 3, you can easily find for the LCM here, which is the same as 3 all divided by 3. Then I'm going to have this 1 over 1, so 1 goes into 3 times, so 3 times 1 is what? 3. This goes to 3 minus 1, so minus what? Lambda, or into bracket c to be equal to, go from 0 to 1, t f of t dt. Now let's divide both sides of the equation by 3 minus lambda divided by 3 on both sides. So here becomes c to be equal to 3 divided by 3 minus lambda, integral from 0 to 1 t f of t dt. So since this is a constant, you can easily what? Send it inside the integral sign. It is a constant. So 0 to 1, 3t divided by 3 minus lambda f of t, so all times what? F of t dt. Now let's substitute this c into the equation we had as a solution to the integral equation. Y of s equal to f of s plus lambda s c. We're going to bring the c back to this side. So y of s becomes f of s plus lambda s plus lambda s, then a c, which is this integral from 0 to 1 t f of t dt. So y of s the same as f of s plus lambda s, then the c, this is the c. I'm going to have integral from 0 to 1, then 3t divided by 3 minus lambda f of t dt. Alright, in the resolvent kernel, we saw that the solution to the integral equation becomes y of s to be equal to f of s plus lambda integral from the a to b, then the resolvent kernel s t lambda, then f of what? T dt. Then let's rewrite this equation to suit this equation. So we can, let's set this s here into this another integral sign. So this one becomes, this equation becomes y of s become f of s plus lambda to go from 0 to 1. So we are sending this s into the another integral sign. We can 3s t divided by 3 minus lambda f of t dt. And can you see that these two equations correspond to each other? Y of s, f of s, f of s. We have our lambda here, lambda here. The limit of t a to b, we have 0 to what 1. Now, can you see that this gamma of st lambda, which is the resolvent kernel, will be the same as this whole this whole part. So the gamma becomes this gamma of s t lambda becomes 3, which is the same as 3s st divided by 3 minus lambda becomes our resolvent kernel. Resolvent kernel. So this is our resolvent kernel. Now the question said we should also find for the radius of convergence. Alright, to find for the radius of convergence, let's manipulate this. You can from the method of approximation, can you see that our kernel from the question given was what? Is st. St always becomes the first term, the first term in the resolvent kernel, which is the same as the a1. And we said that if you are it looks like a GP. So if it looks like a GP, let's rewrite this thing as let's divide both here by 3, divide here to also by 3. We're going to have st to be st divided by 1 minus lambda over 3. Since it's a GP, you know that lambda sum to infinity is the same as a1 divided by 1 minus what? R. So if you compare this and this, you can easily see that your R is equal to the ratio of what progression becomes st divided by lambda over 3 becomes lambda divided by 3. And from the radius of this is the radius of progression. Now let's find the radius of convergence. So for the radius of convergence, the ratio is less than what? 1. So R is less than 1. So absolute value of this lambda divided by 3 should be less than 1. So absolute value of lambda should be less than what? 3. So this is the radius of convergence as we saw in the opposite method using the kernel. Now let's find the solution to this integral equation. We said our solution is of y of s equal to f of s plus lambda, then integral from 0 to 1, then the kernel f of t dt. So we're having y of s to be equal to f of s plus lambda integral from 0 to 1 3s t divided by p minus lambda, and f of t dt. Then we are given what? The free term, which is known, and lambda, the investigative parameter is also known in the question. Which is the investigative parameter is given in the question as 1 over 2, and the free term f of s is given as 5 over 6x. So let's put, and so my lambda is 1 over 2, and the free term f of s is given there as 5 out of 6x. I have f of t here, so you should know that you have to change the variable here to t to get our f of t. So f of t becomes 5 out of 6 t. Now let's substitute all this equation into what? This. So y of s becomes the free term f of s, which is equal to 5 out of 6s plus the lambda, which is half, taken from 0 to 1. So 3st divided by 3 minus what? Lambda. Lambda is half. Minus half. Then f of t, this is my f of t. So this one, the whole of this times f of t. 5 out of 6 t. Then what? dt. So let's evaluate this integral. So here becomes y of s to be equal to 5 out of 6s plus having 3, I can make 3 times what? 3s and what? 5 over 6 out. We have half times 3s times 5 out of 6. Integral from what? 0 to 1. So t times t will be t squared dt. So 3 minus half becomes 5 out of 2. So we can still bring this one to outside. So here becomes y of s plus 5 out of 6x plus 1 out of 2 times 3s times 5 out of 6. Then here reciprocal, interchange it, times 2 out of 5. To go from 0 to what? 1 t squared dt. So our next part becomes y of s to be equal to 5 out of 6s. These two will cancel these two. This 5 will cancel this 5. And here 3 will cancel this one 2 times. So it will remain s plus s over 2. Integral from 0 to what? 1 t squared dt. Equation becomes y of s equal to 5 over 6s plus, if we integrate this, we're going to get t cubed divided by 3. So I'm going to have s over 2 into bracket t cubed divided by 3 divided from 0 to 1. So wherever you see t, replace it by what? 1. And if you put 0 here, the whole of this term becomes what? The whole of this becomes 0. So our equation becomes y of s 5 divided by 6s plus s divided by 2. Then here becomes 1 out of 3. So y of s is the same as 5 out of 6s plus 2 times 2 is 6. So s over 1 6. If you add these two terms, we're going to have 5 over 6 plus 1 over 6 is the same as 6 over 6 into 1. So it's the same as x. So this y of s is equal to s, the solution to the integral equation, as we saw in our previous video using the approximation method. So you can easily see that the approximate method approximates it. The approximate method is the same as the exact solution. So this is the end of this